All right, everyone, thank you very much for coming. We know it's midterms season, so we appreciate you giving us some of your precious time. Today, we're going to be doing a very short presentation, just about a couple tips and tricks that you can use to actually improve the performance of your machine learning models. And after we do that, should be about 30 minutes. We'll give you guys the time to work on the guided project, ask us any questions, or you can also skedaddle early if you, like I said, have midterms. So that in mind, I'm going to go ahead and bring up the first topic, which is going to be transfer learning. So is that you, Sparsh? Yes. All right, so Sparsh is going to be taking over for me on this one.
So the idea for the models that we've discussed so far, right? You're creating every step of the architecture yourself, and then you pass in your training data and so on. But for bigger models, you'll typically need more data, right, in order to make things work properly so that we can capture trends better. But supposing that you don't have enough data, or supposing that the model that you need is actually very complicated, there's sometimes not enough data to make things work the way you want to, so that you can capture all the trends that you want with your model. So to help with this, there's something called transfer learning. So, as I said, deep learning requires lots and lots of data, but sometimes you don't have the data that we need in order to make our models good. So what we do is we take a model that's been trained for a similar task, and then we can take that pre-existing model, and then we can just sort of tinker around with it, repurpose it, and then we can then train it for task B. So the idea is that because it's trained on some sort of related task, task A, then it'll detect certain features that are useful for task B. So this is sort of a visualization of what's going on here. So this is the initial model, the one that we're going to be borrowing. And you can see that all of these are layers that have been trained. So what we'll do is we'll just scrap the last three, because the last three are typically going to handle more specialized functions. And what we want is just the general sort of knowledge that the model has. So we'll just scrap these last three layers, add on some of our own layers, and now we've got our other model, model B. And what we'll do is, because we want to keep the general information that our model has learned, we won't actually do backpropagation and on these. So the gradient descent will only apply to these extra models we've added here. It won't add to these models. So these will be what is termed frozen. So that way, now we've got a model that has insights from sort of the general domain in which the task resides. But the specifics of what exactly we want our model B to do are going to be determined by these three extra layers right there. Right. So now that you've seen sort of a visual representation, we can look at the pseudocode of this to sort of get a better understanding of what exactly is going on with that. So you can see the initializer pre-trained model. Then we'll have some lines to remove the ends of model. That corresponds to that middle section, right, where we take out the last three layers from our initial version of model A, and then we add on a couple of full connected layers at the end. In this case, it's one, but obviously you can add as many as you want, and it'll pass the one, and how much of the model you want to be. And then if we go into our feed-forward network as well, what you'll see is that we freeze the weights. That's what this no grad means. You'll see this function as well when you're adding testing data, right? No grad means that you're not doing weight data set, but you're just freezing the weights for this initial version of the model here. There we go. So that's transfer learning. Very simple in essence. You just have an initial model, take out the last few layers, add your own, train it, but only train the last few that you added.
Oh, and before we move on to learning-based scheduling, I want to add a quick thing about transfer learning. I can go back a little bit. So you may be wondering, how is this useful? Why do we care about transfer learning, right? What's the point of transfer learning? As we have said, it works really well when you have very few data and you want to still be able to perform things like classification, for example, based on this few data. However, what transfer learning nowadays is used in a way that is a little bit different, or a little bit more generalized than our initial notion of train model on some data, use it on some other similar but related data. Specifically, who here has heard of the word foundational models before? Can I see raised hands? Okay, no one has raised a hand. However, who here has heard of the word large language models before? Right, we see a lot of hands down. You may be wondering, when we think of things like large language models, we think of terms like ChatGPT, right? Like, these are models that seems to have a very specific task, which is, given what you have already inputted, what would the next output be? It's a procedurally or like recursively generating task where you're trying to basically predict the next best token, right? Why do we call these large language models when they seem to do something very, very specific? The reason why we call them large language models, as the name may imply, is they are models that are very large and that encodes something intrinsic about language that we can then use them for many what we call downstream tasks. Essentially, what we would do is we usually will train a really large model on a really, really large data set. So you can think of like large language models being trained on just like text on the internet, right? And the training task will typically be something like, say you have a bunch of words, predict what the next word will be, or something like you have a sequence of words, we randomly mask out some of the words and we ask the model to predict what those words will be. And as the model is being trained to do those tasks, it necessarily has to start quote unquote understanding language. It has to be able to start looking at these texts and being able to extract meaning from them to be able to complete these sort of tasks, right? So now we have this model where its output may be something called an embedding, which we'll talk about in, I think, 2 workshops. But essentially, it is a vector that is able to capture the meanings of your input words, right? So suddenly you have this really large model, which is able to not just extract context, but also to extract a lot of information from whatever input you have given it, because the kind of really generalized task it is trained on, what we call, kind of unsupervised / semi-supervised learning. The sort of task it's trained on, it's meant to do things that are very unsupervised, but it's a task that requires it to understand whatever mediums it's trained on really well. Then what we can do is take that existing embedding and then use it in downstream tasks, such as we use that embedding to help us generate the next word, what the next word's supposed to be. Or we can fine tune the model, aka take the model and then train it even further, but on much fewer data sets, to say, I want to generate more lectures by Professor Egger because I love him, right? Stuff like that. So like, this is what we mean like nowadays a lot by transfer learning. And the same thing works for like computer vision data sets as well. Like, we have these huge computer vision models which are trained to do classification on really, really large data sets. Like I mentioned last time, ImageNet, right? There's like 1 million something images. Because it is able to classify those 1 million something images, seeing a really wide range of images. If you remember, the very last layer of that model is our final classification layer, right? The very last layer, and it gives us a 1,000 dimensional vector, which maps to the 1,000 classes. However, what we can do is we can look at the outputs of the previous layer, or maybe the layer before, and because it must be able to take information from those layers, and then do the final classification, we can assume that the outputs from these layers are meaningful in some way and represents our input image in some way. And that vector, that sort of second last layer or third last layer, is going to be helpful for us to do other downstream tasks. For example, what I can do is I can say, use that same model and then put it on a slightly more specialized data set. For example, I just want to classify cats and dogs, right? What I can do is then say, I put in a picture of a cat, I look at the outputs of the second last layer, and I do that for every single image in my data set. Then I have what is basically a really lower dimensional vector that is mapped to a label of a cat and a dog. Then I can then put that resulting vector into a much smaller neural network, like a normal multi-layer perceptron, or like you remember the matrix multiplication linear networks. We can put in a much simpler network and then train that instead, right? That's what transfer learning is. It is the idea of having this really large model, having this pre-trained model, as some of you may have heard, that is able to extract information really well, and we use the information that is extracted typically by its features within its intermediate layers, or outputs from its intermediate layers, and we use that as our kind of extracted information to then train a much smaller model downstream. And because these vectors themselves have already done the vast majority of that information extraction for us, we can then train the downstream model that we train can be much smaller and also be trained from less data, because most of that information extraction work is done for us. Heuristically, all they have to do is interpret that data and say, oh, if say the vectors are around this sort of distribution, it must mean it's a cat. If it's around this sort of distribution, it must mean it's a dog. Does that kind of make sense? Yeah. So that's why transfer learning is very important, because that's how a lot of like AI services nowadays work. Like if you have seen for example, like here is a specific, like machine learning model that's able to generate images of like this specific artist, which is very problematic in and of itself. But like the existence of those things is based on the idea that you can use transfer learning. You can use these pre-trained models and either further fine-tune them or only fine-tune the last few layers to be able to do more specific tasks that the models were not necessarily designed for, but they were designed for a more general task that was meant to do more things, if that makes sense. Okay, cool.
And then one other thing with transfer learning is that you might ask why it's sort of a valid procedure to remove these last few layers, but like have these layers be there, and for that model to still sort of retain that information that it's learned about whatever general task we have. And the reason for that is that these back layers in general, in a very sort of rough and general sense, are more responsible for large scale information, for broader representations of the information. And you see that these last two layers tend to specialize. So the more layers you add on, the more specialized each layer tends to be. And there are ways that you can sort of measure how sensitive each layer is to the input, and ways to measure how they'll change depending on what each layer is looking for. And generally what you'll find that these last two layers are looking for more specific, more complicated things. That's why you can take these out and still leave these things, which are looking for more general patterns, and you can still retain that representation of the information that you've learned. And that's why you can then add these other layers and apply to other tasks. Okay, next up we have learning rate scheduling. Oh, yeah, sorry. So they are absolutely essential, but they're essential to the task that they were trained on. So the idea is that we're taking these models that have been trained on not the task we want, but a related task. So these back layers are going to be essential to that task, that other task, that separate but related task. So that those back layers are going to be a representation for the information you need for that specific.
Another like way to intuitively think about this is like if we have, say, again, a model that's trained to categorize like just a bunch of different objects, and you wanted to do a very specific thing of, say, cancer detection, for example. And like the original model was not trained on cancer detection, but it's a similar task in that they're both like sort of vision models, right? So maybe the first few layers will be doing things such as, is there an edge in this specific part of the image? Is this image bright or is it dark? Are there, say, circular patterns within the image? These are all information that in the original vision model is the sort of layers that are closer to the outputs will then interpret this information and be like, what does this mean? If you say like two circles in these exact parts of the image, maybe that's a person, for example, right? However, say if we were to try to fine tune or like use transfer learning on say cancer detection, then these back few layers are given this information. And again, this is like very heuristic, it's just numbers, we're trying to interpret it ourselves as well. But it's given this information, and it's basically saying, okay, what does it mean for certain circles to be here, right? Because you have this kind of paradigm of information of, we have all these features we have extracted with the previous layers, and we have the final ground truth label of, does this person have cancer? So it is able to make that link. And this is faster than, say, training everything from scratch, because it has this leg up, it has this like kickstart of like, here's how you can extract information from an image. And now I've given you all this information, it's time for you to figure out how then I can use this information that has already been extracted for these, the back layer model, or like the output layer, the new thing that you're training, to do some downstream tasks, such as, classifying cancer. Does that make sense? Okay, cool.
I was just now looking for like, I had a visualization like open like for something else about like specificity. I'll pull that up when we're in the workshop so that you can like sort of see get a more concrete like visualization of what like the specific things the final layers might look for. Any more questions on transfer learning? Because again, transfer learning is also extremely important, because by and large, for most tasks, we're going to be doing transfer learning because you want to do complicated things, but you might not have enough data. So transfer learning really is very, very key to like just using AI like in the real world. So any more questions on transfer learning? Okay, learning rate scheduling. So we talked about this a bit in the very first lecture and then also in the previous one, where we talked about the learning rate, which is the rate at which the weights and biases are being adjusted, right? When you do gradient descent and you have the optimizer adjust all the weights and biases, it's doing that according to some sort of learning rate. That's the, you can think of it as the size of the step that you're taking in the loss landscape. So if you can look at these visualizations, what you'll see is that if you have a low learning rate, you'll be taking really, really small steps. So you'll take very deliberate sort of steps. But if you have a really high learning rate, what you'll find is that you can get through like some sort of local minimum much faster. But because your steps are really big, you might not ever end up here. You'll just sort of like bouncing around close to it, but you might not like ever really get it. You just keep overshooting because your steps are big. So what we'll want is ideally some sort of balance between a really high learning rate and a really low learning rate. So initially, we'll want to have a high learning rate because we will most likely be very far from the minimum, and we want to take large steps so we can get to the minimum. But at the end, we want to take smaller steps so that we can, avoid this. Can you see my? Yeah, you can. So that you can avoid this sort of situation where you're taking really big steps, but you're like trying to get to the minimum and you can't because your steps are too big. So you'll make your learning rate smaller as you get to the end, which we can sort of see here. Epoch, the word epoch refers to the number of times that you go through every single sample in your training data, right? So if you have a batch of say size 60 and the total training data has size 240 images, then you'll end up with 4 batches. You get to the end, and of your training set, that would be 1 epoch. So as you can see, as you progressively epochs, what we want to do is drop your learning rate so that way you end up taking smaller steps as you get closer and closer to the minimum. So this line that we saw here is following some kind of curve, right? And there are lots and lots of different curves that we can have the learning rate follow. The simplest thing would be just as you increase the epochs, just drop your learning rate linearly. And then you can also have more specialized things, right? You can have it drop step by step. That's what we have here. It's kind of sort of. You can have an exponential decay. You can have a time-based decay, and all sorts of other things. And you can also combine these functions, right? Like in the one that we saw previously, it was sort of a combination of step-based decay and also exponential decay. So as you can see, generally what you'll find is that time-based decay for the learning rate tends to work really well as constant based decay. But all of them sort of, you can see, are not too far from each other aside from exponential decay, most likely because you're making the learning rate fall too quickly. But other than that, you can see that they seem to do reasonably well. And they, in fact, dropping the learning rate is going to make your model better. It's gonna, the final state that its weights and biases are in, you're gonna find that they are more optimized because you're making sure you're getting to a local minimum fast enough and you're not just bouncing around at the bottom. Okay, so any questions on learning rate scheduling? Okay, or any questions about what happens if the learning rate is too high or if it's too low? Okay. And then I'll pass it on to you.
Now we're going to talk about regularization. It's another pretty important technique that you can use to improve your model's efficiency and accuracy at the end. What essentially regularization is, it's a way to decrease the complexity of your model. So usually when training a model that's too complex, you go into the issue of overfitting, which is essentially when the model is so good that it memorizes the training data, and so it sort of lacks the ability to generalize unseen data, right? So these are some examples of one model trained on the same data, but with a good versus underfitted or overfitted. It could fit a robust fit because it does match the data flows pretty well without overfitting and literally touching the data printer. There's a good margin. So this is a good robust fit. While this is an overfitted model, as you can see, it's almost perfectly fitted. But if we were to probably generalize this and bring out some validation and testing data, this would do pretty bad. So yeah, that's what overfitting is, and regularization fixes this issue. So this is an example of a model overfitting. As you can see right there, the orange is the testing data and the blue is the training data. So the training data is, in this case, this is the F1 score. As it increases, it gets better. So the training data here is decreasing and the accuracy is increasing, but the testing data sort of plateaus around 12.5. I think it's it's probably like epochs, around 12 epochs. And around this point, it started to overfit the data, meaning that the model's complexity isn't allowing the model to generalize to unseen data. And usually it actually goes the opposite way. So I hope you guys can see this. Can everyone see this? So usually it goes the opposite way, right? So the training accuracy gets better and better and better. But if you keep on training it, it goes down. Because what happens to the model is that it gets so good at learning from just the training data that it becomes pretty bad at generalizing to the unseen data. And that's basically what you want your model to do, is just generalize, right? Because it doesn't really make sense if you're only looking at one training set. You want it to generalize. Yeah. And so just to give you guys a few techniques we can use to combat this overfitting, one is L1 and L2 regularization. We'll get into that. It's basically putting a term in your loss so that you can dictate the weights in sense. And another is architectures. Some architectures have their own inherent regularization. One example of this is a ACM, which has a pretty good amount of regularization. Just because of the decrease in the number of weights, it requires you to sort of understand the image more. And as it looks at, you guys remember we talked about the kernel looks at local features rather than looking at global features. So this allows you to actually generalize to multiple different data. That's why you can consider some architectures actually as having inherent regularization. Another is block regularization. We'll also talk about that in the augmentation. And another is to simply just decrease the complexity of the model, right? So let's say, for example, you have five hidden layers let's say you have a feed-forward neural network, you have 5 hidden layers, just decrease. And it's helped me out so much. Like I've seen a huge increase like this, decreasing the complexity of the model. So yeah, like I've personally seen this as well. We do this sometimes. It works. And so to start with the first one, L1 and L2 regularization. So essentially with L1 and L2 regularization, they add penalty terms to your loss function, right? So this is L1 regularization. We're adding the sum of the absolute value of the weights, and for your L2 regularization, taking the L2, which is the square root of the weights. There is a very subtle difference. Even if they might look the same, this is square, this is an absolute value. This is hard to differentiate when you reach zero, right? Because it's an absolute value. It's pretty hard to differentiate when you reach zero. I guess not very hard, but it does make it a little troublesome, while this isn't. And so usually we do use L2 regularization, sometimes we use L1. Yeah, so why does this work, right? Why does this help in reducing models of effectiveness? Well, because what it's essentially doing is it's taking your weights and decreasing their importance. It's pulling the weight vector to the origin so that when you do train the data, your weights don't have as much significance. So because sometimes you just might have too many parameters, right? You need to sort of have a cost on each of those parameters. So it's saying that if your parameter, it's sort of a balance between your loss function and this penalty, right? And the way we control this balance is by adding a lambda here. And this lambda, for example, if it's one or if it's a large value, what it does is it puts an effect on a larger effect on the penalty term. So then all your weights are zero, and that's not what you need, right? If it's too small, this is pretty much useless, right? Because in that case, you're not really looking at the weights anymore. You need that, so you need to, as this is a hyperparameter, you need you need to start testing and so on to get the correct values of lambda. And this helps a lot of the times. Does anyone have any questions on this? And data augmentation. Now, data augmentation is probably one of my favorite regularization techniques, specifically because it seems so simple, but it helps out so much. What you're doing is you're simply taking the data and you're transforming it somehow. Right? Let's say you have an image of a cat, for example. You locate the cat at some new data point. You can crop the cat. You can like strike the cat. You could maybe even change the color a little bit of the cat. All these are new data points, right? Suppose you started with a data set of maybe 10,000 data points, you could quadruple it, right? Just by augmenting the data. And it might seem that this might not work because it's the same cat, but it does. I've also trained neural networks on this, on the same variant, the dog and cat data set. Just by augmenting it, I think it went from like 75 to 80, 85. It had like a 10% increase now, or more. So this helps a lot. But this does have one big issue. And can anyone guess what it is from reading it? Negative of data augmentation. Yeah, but why? Yep, exactly. Because there are more images, you need more training time, right? And so that's one trade-off. So you have to have a balance between augmenting the data, you know, how much do you want to augment the data and how much do you want to, yeah.
Does this mean that we can just arbitrarily increase the size of our data set by just like copying multiple times?
Yep. You can do that, but it's not. So there's a trade-off, right? So suppose, for example, you just keep copying the cat. You can't just copy it forever. But at the same time, the model's not, the improvement isn't going to be as good as you want after a certain point. There's like a balance that you need to keep between augmenting the data and actually displaying. Not just keep the data.
So would it be overfitted for this specific basically to it's like it because like said that one of the conflicts is that we don't have enough data sets. This is that increase the data set as much as you want.
Yep.
Yeah. So is it just that so basically we don't do that as like it would matter.
Yep, exactly. It would, but you made a really good point. You might even overfit it. If you're just taking an image and having different versions of that image, the model might learn to just look at that image rather than the actual general. You see what I mean?
So yeah, so it is technically the same.
It's like a fundamentally different data frame. For example, this image, you can't see the head of the cat, right? So the model to learn how to differentiate, I guess, this versus that, it would be a totally different image, even though they're the same thing. You see the reason?
If it's a completely fundamentally different data pool, why does it cost so much?
But at the same time, I see what you're saying now. At the same time, they do have some varies. So for example, the model might learn, okay, if like, you know, the foot has a certain, like if the foot has a black stripe, to make it a cat. Just because it's seen the same cat over and over and over and over again, and those cats have similar. Even though it's not.
Yeah. Just another quick thing is like the whole purpose of data augmentation is also that we want the model to be invariant to things that to us doesn't make a difference to the image, right? We don't want the model to be relying on that, oh, a cat must have the head in this specific position. We're moving around and flipping it and cropping it and sometimes even adding noise to the image, making the image a little bit different, darkening the image, brightening the image, the contrast of the image, stuff like that. We're doing stuff like that because to us as humans, that's still a cat. And we want the model to be invariant to these what we call kind of like noise, right? We want it to be invariant in the sense that even if we add a noise to our input like this, it's going to be okay with it. It's going to classify it as the same. So it basically diversifies the data set because then the model is able to look at images that are quote unquote out of distribution in the sense that this is an image that maybe doesn't look perfect. This is an image that maybe is the subject isn't centered. So we're widening the distribution of the images, but we're not widening it to the point where we have complete like new data, right? New real world data. It's different, right? You're gonna see how that's different because that's like actually having a completely different object. Another thing to remember is that these are being read. We're feeding these images CNNs, right? Their filters is being dragged across the image. What we're doing here is also kind of encouraging the CNN to actually also be able to kind of learn that we're invariant. CNNs already kind of assume that we're looking at local features only. We're kind of just reinforcing that. Does that kind of make sense? So that's kind of what's going on next.
If you zoom in through that, something and we see then it starts like bubbles.
Yeah. And in this case, excessive augmentation, in the sense of like we are changing the integration that in that even us have difficulty recognizing the original image is. Because typically for data augmentation, the way it's implemented, there really isn't a excessive augmentation in the sense that as long as you set limits for how much content, how much you should, you're going to be okay. And like specifically, usually what we do is instead of what you can do is kind of like pre-process your images, kind of just like double your data set by just doing a single augmentation thing to every single one of the images. Or more commonly, what you would do is during training, before you pass your actual images into the model, you do like an augmentation pass on all your images. So it's every time it's random. It's a random crop, random location, random one that you're doing. So it's technically we're almost like your data set is infinitely large because we're doing this random operation every time. But realistically speaking, it's just still our data set. So then we're forcing the model to be invariant to these methods. In a way, we're kind of forcing the model to be going to a minimum that is flatter, right? Going to the minimum that is less sensitive to our initial condition or initial image. That's why like all these techniques that we're teaching, like later networking, but both like all these like transfer and optimization, they're all techniques that can help you go. It's really easy to overfit it now, especially if you have a sufficiently large model. It's really easy to learn, and especially if your data is covered, it's really easy to overfit on them on the training set. How can we mitigate, right? Because the training data set kind of sets what the maximum point, what the ceiling of your code is. Like even on the edge of that task, like last time I was showing you, I was like, oh yeah, they got to 3% error. However, on the training data set, they got to like 99% error years ago. It's really easy to overfit the model, but it's really hard to make sure the model also generates this repetitive. And this is one of the ways we're trying to emulate that. If that makes sense.
Oh, real quick, does anyone remember why we prefer have shallow minima as opposed to having like minima that are like really steep, like little like dips in our loss landscape?
That means that it's done.
Yes, it's very close. So that has to do, as you said, we don't want to be rigidly constrained for fitting it. So if what we're seeing is going to be like a really, really big dip, but that's a really brief dip in our loss landscape, what that tells us is that this is a quirk of our training data. This may not be present in the actual data in the world. So if you see like tiny little features like that in the loss landscape, that may not be reflective of actual data in the real world because it's such a little brief quirk that it might not exist once you like add more data points, and then that would change the loss landscape. This loss landscape is dependent on the training data. So that's why we got to make sure that when we're navigating our loss landscape, we're not just thinking about the loss landscape that we're actually in, but the loss landscape if we had like all of the images in the world. And we want to make sure that we get to a minimum that sort of works in all cases, in generalized cases, not just a very specific.
Add to that, this isn't the only place that you can use. Images aren't the only place that you can use data augmentation. Another place is with audio. Audio, you can take the same audio, you can increase the frequency. I guess frequency is a little hard for amplitude and so on. And you can manipulate the audio in a way that it's still the same, but it just might sound different. And you can train your model on that, and that might help. Yeah, don't quote me on the frequency, more than amplitude. So another way is called dropout regularization. In this case, this works by turning off the nodes in your network, right? So the nodes that come with the neuron as you're going through one path, but they don't have an effect in the network. So their intention is propagating a zero value, right? And what this does is it prohibits them from creating a codependency, generalized pattern, right? So you guys remember last time we had a dropout layer where we said, oh, between this and this layer, turn off 10% of the neuron, 0.1% of the neuron. And this also helps it because the model learns how to take sort of different paths through the neural network and see the general pattern of the data, rather than specific pattern of the data. And this also does randomly, so that you're not always turning out this node again and again and again, or you're not always turning out this node again and again. It's not. Yeah, does anyone have any questions on this? So now to come to a different problem that's very related to regularization, but it has a little bit of a difference, the vanishing gradient problem. So this is when your gradients, as you propagate back through your neural network, they vanish, they become zero. So I would suggest anytime you guys are training a neural network, and if you're running to the problem where you're not really seeing an improvement when you should be, like there isn't an improvement in the output of your neural network, always just print out the value of the parameters and then print out the value of the gradients, right? Because then you can check how, what are the gradient updates for my neural network. If the gradient updates are really, really, really low, especially as you go back in your neural network, that means that you're probably going through a vanishing gradient problem. And the reason for this, the reason for this is because of the fundamental way like that the ear is calculated, the derivative with respect to the ear is calculated, and as you go back through your neural network, the gradients are multiplied, right? So if you have an earlier layer and a later layer, and if the later layer's value is less than 1, for example, right, and you multiply the gradient by each other, what's going to happen is it's going to decrease, right? You have 0.5 multiplied by 0.1 and so on, it decreases and it vanishes. So the effects of these earlier layers are going to be minimized. So you can't really use that as much as you want to use it, right? And some ways to solve this issue, one is to reduce the depth of your network. Just reduce it. It's this simple. It helps, like 74 times it helps a lot reduce the depth of your network. Another thing is gradient clipping, right? So essentially, once the gradient is past a certain point, just clip it, right? And well, that's what another batch normalization. We talked about this last time, and essentially between every single layer, you're going to take the activations of one layer to the other layer, and you're going to normalize that based on a distribution. So you're going to find the mean and the variance of it, then you're going to normalize it so that the values are they follow some sort of normal distribution, and that helps in preventing the vanishing gradient problem. Another is residual connection. You just take take the layer, put it through some type of architecture, and just take the same value of the layer, concatenate it, or like add it up at the end. And this helps decrease the vanishing gradient problem because now the gradient has two ways to flow. One through this architecture, and another through the previous architecture. So it helps decrease the gradient, vanishing gradient problem. Does anyone have any questions for this? Yep. Yep. Yep, that's an excellent point. That's also a really good solution. Is to use rarely, which is the rectified linear units. And the reason why, and that's a really good. I can't draw this. The reason why it's a solution is because unlike sigmoid, for values of x that are greater than 1 and so on, sigmoid essentially makes the difference very small because it flattens out, right? But the ReLU doesn't. It's a linear function from 0 as you go on, but before, for values less than 0, it's a negative function, right? So it allows you to have gradients that aren't as small. But with the sigmoid, you're going to have very small gradients. That's a really good point. Yeah. Yep. So this also works with what's called exploding gradient problem. But once the gradients go past a certain point, just cut them. Don't let them go past a certain. So this is like a boundary, right? So if you go past this, oh, you're not going past this. If you go, no, you're stopping them right there. Yeah. You gonna have any other questions? All right. By the way, good question, guys. And so, yeah. So this is the exploding gradient problem. It's the same thing as the vanishing gradient problem, except you're going the other way. Now, the value of the gradient is greater than 1. And so, you have the issue of the gradient at the end will be like some gigantic number. You're like, wait, why is this here? And so one way to fix this is using gradient clipping. Said that. Another way is proper rate initialization, right? So we haven't really talked about this yet, but it's extremely important the way you initialize your weights in your network, right? So usually, like the rule of thumb is to initialize your weights between -1 and 1, and PyTorch already does this for you. But there's like sort of better ways in some cases that you can initialize your weights. One way is called Xavier initialization, right? Where you take into account the amount of connections that's coming to a neuron, the amount of connections that are getting out of a neuron, and based on that, you initialize the weights. Because good weight initialization can improve your model train drastically. That's another way. And again, batch normalization. Use this, guys, because this helps me drastically. Like if you look at the original paper for batch normalization, not only does this help prevent all these things, but it also helps speed up your the performance of your neural network, because now the values between the layers are normalized, and so it becomes much easier for your neural network to pick up on general patterns. Improve. So yeah, batch normalization is a very, very important technique. And if you guys haven't seen your guided project, I would suggest you use this. And this image just gives you a sense of like how. Oh, I forgot to mention. Also, lower learning rate help with the exploding gradient problem. Because if you have a high learning rate, what happens is you overshoot. And sometimes, in some cases, when the learning rate is so high, you not only overshoot, but you cascade towards infinity. You just keep on getting larger and larger and larger and larger and larger until it's useless, until the computer can't handle it anymore. And so lower learning is also a very helpful thing. And again, print out your gradients, and you can see if this is a problem. Yep. So that's it. Does anyone have any questions on this? Okay. So momentum.
Alrighty, I'm back. So as you guys hopefully remember from last week, we talked a little bit about momentum, where basically the idea is, right, gradient descent is only going to be looking at the current location and really nothing else, right? And this can be pretty good some of the time, but other times we want to get, a little bit more of a bigger picture. We want to look at how the gradient has been behaving so far and use that to inform our decision. So that way, if there's, small like features, like think about it like if you're rolling like a ball down the hill and there's like a small bump, the ball should just like keep going over the bump instead of like getting to the bump and like shooting up, And so that is what we're trying to achieve with momentum, right? So like if, for example, we've recently been, descending very quickly, and then all of a sudden there's like, an increase, we probably aren't randomly at a minima. This is more likely just like a local terrain feature of the loss landscape, right? So quick little refresher that everyone kind of remembers what's up with momentum and all that. Good. All right, beautiful. So now on to Nesterov momentum. So there is one big problem, well, not a huge problem, but it's a decent sized problem with momentum, which is how does momentum tend to behave when we get to an actual minima in our loss landscape? Anyone know? No idea. It says up there. So all right, well, so when you're using momentum, right, you're going to tend to overshoot your minimum, right? If you've been going down like a slope or whatever and you're, trying to reach your minima, when you get to the minima, because you have the momentum there, you're going to continue going forward a little bit farther past your minima, and then like, hopefully you'll come back down and eventually like you'll settle down there. But it's a little bit inefficient. And so this is where the idea of Nesterov momentum comes in. So originally with the momentum formula, if you guys remember, this is like the math notation for it down here, but essentially we take our old momentum term, right? And then we go and we change we use that to inform where we're going, right? And then we update it based off of the gradient where we're currently at. We're like, okay, we're going to keep following the momentum, and then now we're at this point, and so the momentum should be adjusted by like this much, right? But what you might notice is that we can actually not necessarily go to the location and take the gradient there. What we can do instead is calculate where the momentum wants to take us and then calculate the gradient. So if you look up there, right, we have, you know, these 2 points, like the blue and the black point. And say if we're at the blue point and the gradient or the momentum is saying that we want to end up at the black point, the gradient at these 2 points are very similar. So it's going to behave pretty much the same whether we are looking at the gradient at this point or the gradient at this point, because either way it's a relatively steep gradient, or well, in this case it's just the slope, right? But it's relatively steep, and so our change to momentum is pretty much going to be the same in both cases, right? But if we do this method of Nesterov momentum where we're looking ahead to where the momentum wants to take us and then taking the gradient there, where it really can have some benefits is when we reach a minima, right? So as illustrated in this diagram down here with momentum, the momentum would take us all the way down, and then we'd just kind of like leap across to this point over here, right? But if instead we're using Nesterov momentum, as we're going down here, as we talked about right on the previous slide, we're going to tend to have the same behavior because, you know, we're going downhill. But then we get to this point, and instead of jumping here, we say, okay, well, the momentum wants to take us here, but I'm going to look ahead and see that here the gradient is actually going to be moving us backwards. So I'm going to update the momentum based not off of jumping here and then taking the gradient, but I'm going to say, okay, here is what the gradient would be like, and so I'm going to modify our momentum by that much and sort of like cut out this step. Does everyone see like kind of get like the intuition behind that? And so basically what we're doing with Nesterov momentum here is it's allowing us to preempt some of this overshoot of the minima in the loss landscape, where instead of shooting all the way past, it's going to be like, oh, this wants us to go and shoot like a little farther past. We're going to like step back. But, or yes?
Will you finish?
Or no, go ahead. Yes. So the way that this is going to behave is sort of like, it's sort of like just damping down the momentum, you know? Like we're still going to observe the same general behavior, right? It's sort of like in between the characteristics of momentum and gradient descent, right? Because as you see here, we like in Nesterov, well, it's Nesterov accelerated gradient descent, Nesterov momentum, same thing. But as you can see here, we're still going forward because we still are making use of momentum. Because remember, we look at our previous momentum and then we update that and we use that to inform where we're going, right? So like here, even though we're like, yes, this is going to move us backwards, that isn't going to send us entirely backwards. That's just going to mean that our momentum is going to decrease, right? Like here, the momentum is larger than it is here because here we're observing a decrease, right? And so, like I was saying though, we're essentially like preempting the overshoot, but it still is going to have those momentum-like characteristics where if you encounter like a small bump, you know, like if you're going down and then you have like a little bit of like a lip here, right? Your momentum is going to take you down, 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 and take you over and allow you to keep going forward. That's kind of similar to what Nesterov momentum, the way Nesterov momentum is going to behave, because even if the momentum is, you know, decreased a little bit more here, hopefully we're going to have enough momentum to still make it over the hump, right? And so the fancy math way of writing it is shown up here, where essentially we have, so if we compare it to momentum here, we have our constant alpha here times the past momentum minus our other constant epsilon here times the gradient at where we end up, right? But here we're taking not the gradient of where we are, but the gradient of where we're projected to be. Because as you can see, we have our theta term plus and then alpha times the momentum. So basically, go back here, if you remember, theta plus the momentum is just where we would end up, right? So theta plus alpha times the momentum. That's just saying this is where the momentum would take us by itself, and then we're taking the derivative, or not the derivative, the gradient at that location. So instead of taking the gradient where we are, we're taking the gradient of where we're projected to be, and it just sort of like smooths it down. You know, if you see like on a lost landscape that you're coming down and you like overshoot and then like come back like this, you might see with Nesterov momentum a little bit more of like that, right? Where you're not overshooting as much. Does that make sense to everybody? So any questions about Nesterov momentum? Yes. Yes. I think I'm pretty sure it's been proven to be better and it's going to be more efficient, right, Jordan?
Well, it's okay. It's
Oh, there's no. Yeah.
so
Jordan can explain it.
basically like the whole thing with nested momentum is you're looking ahead, right? And you'd be like, oh, we're looking ahead. Does that mean like each iteration we're gonna like do this whole thing twice? Basically, what people figured out is that you can like parameter if you look at what's happening in the current step, you look at what's happening in the next step, you can like map it out in a way such that you can basically take the previous step and just like you kind of put it in the next step, and basically it's just the same like computation complexity as any other like momentum algorithms, where you're doing this like extra term when you're applying the momentum, and that extra term mathematically will be equivalent to if you were to say look ahead. So that's basically kind of how it is. Yeah. Does that kind of make sense here? Yeah. So again, like this sort of extra term here, like that's just like it looks like here we're like applying this additional thing, right? You're saying, oh, we're applying this, and we're calculating the gradient. What we can do is take this plus AB and just put it in your previous steps data data calculation, right? Then you may be asking, wait, if we're adding this additional plus AB term, wouldn't it be problematic during actual evaluation because we have this additional AB term that we have added to it that it's not supposed to be there? Well, the idea is that with momentum, when the model does eventually converge, what happens is that when it does converge, this V term should be very close to zero. AKA, even if you're running this, training this model for a bunch more times, we're not really nudging it any further. We're not only nudging it by a very small amount. So doing this won't affect the final data by much because the magnitude of your V will be very small. And if you say we're doing learning and scheduling, usually by the end of training, your learning rate will also be much lower. So your alpha will also be lower. But like this term, at the end when your model does converge, will be very negligible compared to the rest of your model. So you're able to kind of parameterize and basically focus in the previous step with the theta there. That makes sense. Just remember that this is like you're doing this again and again and again with your iterations. That kind of makes sense? Yes.
Quick question: is there any reason not that's the wrong momentum? Like, it seems like a more efficient way of doing it.
There really isn't. Like, people nowadays pretty much exclusively use necessary momentum if they're training classification models. Specifically, they use stochastic gradient with necessary momentum, right? And they do like learning and scheduling because usually it gives you a little bit more fine-grained control over what you can and what you cannot do. However, when you're training much larger, especially generative models, so if you think like like how a lot of large language models are trained, how like DALL-E 2 and are trained, they usually use Atom instead. Because Atom is more stable in that you're less likely to put the model in a bad place. Because these generation-based models, they're usually a lot more sensitive compared to classification models. Due to various reasons that I will also talk a little bit more about when we do talk about it in I think a very last workshop. But basically, for much larger models are much more sensitive to training, and very often you can lead to failed training. We usually use Atom, specifically a variant of Atom called Atom W, which is like Atom with a very specific weight decay thing. Like if you remember before with regularization, we're talking about weight decay, right? Like L1 at regularization, L2 regularization. It's a specific variant of Atom that takes into account the fact that weight decay may want to change the magnitude of weight decay and make it not dependent on the Atom sort of scaling of the gradient itself. So it's just like a very small variant of Atom, but mostly today you will see that most models are going to be trained with Atom. But what we are doing with image classification, you will probably want to either use Atom if you don't want to mess with the habit parameters too much, or if you want to fine tune everything very yourself, use natural momentum. So in summary, Atom is really nice if you just want to start it and don't think about it. You just set the learning rate and don't worry about it anymore. Like you set the learning rate once, you set it to constant, it's going to work fine. However, if you want to push your models to the next step by training it, maybe at like 5% accuracy, then probably use natural momentum, but you have to be a lot more careful with what your learning rate is and how you schedule it. Does that make any sense? Okay. Yeah.
Yes. Does that mean what is also a hyperparameter? The V, the momentum term, or?
V is not a hyperparameter. V is something that you accumulate throughout, right? It represents your momentum. V is initialized to just all zeros because at the very start of training you don't have any momentum, right? And alpha will be something that, in this case, alpha is your momentum itself. You just set it to that. This is a hyperparameter. Your learning rate, epsilon, is also a hyperparameter. But V is something that you actually accumulate. It is a exponential moving average of your gradients. Yeah.
Anything else? Alrighty, well, I believe that is everything that we have. You're welcome to stick around. We'll be here for, a little bit longer if you want to look at the project, ask us questions, come for guidance. But also, it is midterms week, so, feel free to skedaddle now. If you have any feedback, as always, feedback forms up there, attendance code, our, the QR code, everything's up there. So, yeah, thank you guys for coming.